Welcome to the 49th lecture on computational mathematics with SageMath. In this lecture, we shall look at how to find dominant eigenvalues and corresponding eigenvector numerically. We have seen use of dominant eigenvalue in Google search algorithm, and it has many other applications. So, let us start with an example. We know that Sage has inbuilt function to find eigenvalues and eigenvectors, and it can find eigenvalues of eigenvectors of reasonably large matrix as well. So, for example, if I look at a matrix A, which is a random matrix over integers of 8 cross 8, and let us say the entries lies between -10 and 10, and let us convert this A by multiplying by its transpose. So, A into A transpose will be a symmetric matrix, so all its eigenvalues will be real. So, let us find eigenvalues of this. So, this is what we get. So, you can see here these numbers which you are getting are in decimal and there is a question mark at the end. This simply means that these computations are done numerically. These are numerical eigenvalues. So, how does one find such eigenvalues? So, we will be looking at an algorithm to find dominant eigenvalue of a matrix. So, in this case, for example, let us look at what is the dominant eigenvalues. For example, if you look at here, this set of eigenvalues are by default arranged in increasing order of its magnitude. So, now suppose we sort this eigenvalues and say reverse equal to true, it will be arranged in decreasing order of the magnitude. So, Sage has inbuilt method in order to find the dominant eigenvalues of a matrix. So, if you want to extract this dominant eigenvalue, you can simply say find the maximum of the eigenvalues of this. So, let us look at, if I say max of m dot eigenvalues, then I will get the maximum of the eigenvalues. So, this is what we want to find out using an algorithm which is known as power method. So, let us see how it works. What is this algorithm? So, first of all, let us assume that A is a n cross n real matrix, and we shall also assume the two conditions on A, that A has a dominant eigenvalue which is real and its absolute value is strictly greater than all other eigenvalues, right. So, in case lambda 1, lambda 2, lambda n are eigenvalues of A, then modulus of lambda 1 is strictly bigger than modulus of lambda 2, which is bigger than equal to modulus of lambda 3 and so on. That is the assumption, where lambda 1, lambda 2, lambda n are eigenvalues arranged in decreasing order. Second assumption on A will be that A is diagonalizable. In particular, A has n linearly independent eigenvectors and it forms a basis of Rn, right. Now, what we do is we start with a non-zero vector x naught. You can start with unit vector or start with some vector which dominant entries or the entries the maximum value of the entries is 1. Okay. So, let us start with a non-zero vector x0 and define x1 is equal to a times x0, similarly, and x2 is equal to a times x1 and so on. In general, x to the xk is equal to a times x to the a times xk minus 1. So, that is a iterative scheme. So, in if you just simply simplify this, xk would be nothing but a to the power k x naught. So, we are defining a sequence of vectors starting with x naught as x1, x2, xk and so on by xk is equal to a to the power k times x naught. Now since A has n linearly independent eigenvectors x1, x2, xn, it forms a basis corresponding to eigenvalues lambda 1 to lambda n. This x naught, vector x naught, can be written as linear combination of x1 to xn. So let us write x naught as c1 times x1 plus c2 times x2 plus dot 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 cn times xn. Now apply a to the power k on both the sides. So a to the power k x naught is nothing but xk, and that is going to be on the right hand side, it will be summation ci a to the power k xi. And since xi's are eigenvalues, a to the power k xi will be nothing but lambda to the power k xi, and then you take lambda 1 to the power k outside this bracket. What you will be left with c1 x1 plus summation ci into lambda I by lambda 1 to the power k xi. Now if you notice this, since lambda 1 is the largest, strictly bigger than all eigen values, lambda I by lambda 1 for I bigger than equal to 2 will be strictly less than 1. Therefore, as k goes to infinity, as k becomes large and large, this quantity will go to 0. So what it means is that if you take x to the power k divided by lambda to the power k, lambda 1 to the power k, this will converge to c1 x1, right. And what is x1? x1 is the eigenvector corresponding to eigenvalue lambda 1, which is the largest, right. So this gives you, in case c1 is non-zero, we can write x to the power xk divided by lambda 1 to the power k divided by c1 that converges to x1. So it gives you a way to find out x1, namely the dominant eigenvector. Eigenvalue vector with the corresponding to dominant eigenvalue is known as dominant eigenvector. So, and once you have obtained x1, namely an approximation of dominant eigenvector, you can find the approximation of dominant eigenvalue using this Rayleigh quotient formula, which is x1 transpose a x1 divided by x1 transpose x1. So this is a x1 is lambda 1 x1, so numerator will be lambda 1 times x1 norm x1 square divided by norm x1 square. Since x1 is eigenvector, this will be non-zero, therefore you can cancel this and you have the dominant eigenvalue. So that is what is the algorithm. So in this algorithm, the only thing is that you need to do some scaling, so that this lambda 1 you get as an eigenvalue, right. So the scaling is done as follows. You can choose x0 at every stage, you choose xk in such a way that the maximum entry is 1, right. So you can divide this vector axk by the maximum of the entry in xk and go to the next iterate. Okay. So let us see what is the algorithm. So algorithm is as follows. Start with a non-zero vector x0 having the largest component as 1. So if the largest component is 1, this will be non-zero. Set k equal to 0, that is 0th iterate, and define yk, vector yk, as axk, and then take ck to be the maximum or the largest component of this yk in absolute value, and then define xk plus 1. This should be bracket here, xk plus 1 is equal to 1 upon ck into yk, right. So again, and then check whether this meets the convergence criteria. Now what would be the convergence criteria? The convergence criteria, you can take you can start with some arbitrary positive real number, and in case the difference between two consecutive xk becomes less than epsilon, then you can stop, right. Or if you want to stop after a certain number of iterates, that itself becomes your convergence criteria. Now let us so in case the convergence criteria is met, you have already achieved what you wanted. That means xk plus 1 will be the largest dominant eigenvector, and you can stop. Otherwise you redefine k is equal to k plus 1, that is go to the next iterate and then go to step 3, that is again find out what is Ck, and then find xk plus 1 and so on, right. So, let us implement this. So, let us look at an example. Suppose we want to find the largest eigen value, there is spelling mistake here, eigen value and the corresponding eigenvector of a matrix A, which is 4 minus 5 2 minus 3, starting with let us say initial vector x0 is equal to 0 1 using the power method. So, this method is called power method, and why the name power method? Because you are dealing with a to the power k for various values of k, that is how the iterates are defined, right. So, now let us write Sage routine. For this we will import two functions, argmax and argmin. This will find the index for which a list has maximum value, and similarly argmin will find the index for a list which is maximum, right. Now, so A is this matrix, x naught is the starting vector. Let us look at, we want to do maximum 30 number of iterates, and since each computation is going to be numerical and it will display so many decimal places, let us restrict to only 8 decimal places in each of this coordinate, and the tolerance limit is let us say 10 to the power minus 4. And so, start with initial error which is 1 and initial iteration, that is 0, and then while the I is less than equal to maximum number of iterations, which is 30, and the error is bigger than equal to the tolerance limit, you find out y naught is equal to a times x naught and find the maximum value of the y naught, each coordinate of y naught. So, that is y naught dot apply map absolute value. So, apply map apply underscore map will apply this function to each entry of this list, and then define the maximum of the argument of this, and then take the C1 to be the maximum value of this y naught, and then define x1 to be y naught by C1, and then define the error term as x naught minus x1 in the norm, and then increment this by iteration increment by 1 and reassign x naught x1 as x naught, and then we are simply printing here this yi, ci and xi. This is what is printed. So, let us run this program, and this is what you see. Y naught in the first iterate is this, and then the maximum value of that is minus 5, then you divide by minus 5, you get 1 comma 0.6, and then next one is define y1 will be a times x1, and then says your y1, and then define c1 which is the maximum value, in this case 1, and so on. So, this is what you get. It requires in this case 14 number of iterates. So, at 14th iterate y1 is this, and c1 k, that is c to 14 is 2, which actually will be eigenvalue, and this is the x15, that xk plus 1, this will be an eigenvector. So, that is, and now let us look at what are the eigenvalues and eigenvectors of A. So, A eigenvalues are 2 comma minus 1, and that is what you are getting here Ck, and let us also find out what are the eigenvectors. So, A dot eigenvectors right will give us the eigenvector. The eigenvector corresponding to eigenvalue 2 is 1 comma 2 by 5. 2 by 5 is 0.4, and so that is what you can see here. This is 1 comma 0.4 approximately, right. So, that is how you can apply this method to find dominant eigenvalue and corresponding eigenvector. Let us look at one more example, slightly bigger example, 3 by 3. So, this is a matrix A. In this case this is not symmetric, but one can check that it has all eigenvalues and dominant eigenvalues are is strictly bigger than 1, right. So, again we are just applying in change in the previous syntax is just that we are changing the matrix A and everything remains the same, and then when we run this program, we'll get in this case again we require 14th iterate and 14 iterates, and in this case the dominant eigenvector is 0.499, which is approximately 0.5 and 1, and the eigenvalue is 4, right. So, and this Ck are giving you eigenvalue because we scaled at every stage, that we looked at the maximum of the entry. And okay, so in case this is your eigenvector, so this eigenvector I have stored, you can see here in x naught is redefined, I mean x1 is redefined in x naught or stored in x naught, and therefore we can find we can apply, let us say, this Rayleigh quotient in order to compute eigenvalue, and in this case the eigenvalue is 4.0061, and that is what you have here, right. So, once you get eigenvector, then you can find corresponding eigenvalue with this, using this Rayleigh quotient. And if you try to find out what is the maximum eigenvalue of A, then this is 4, right. So, this is another example, but if you want, you can make a user defined function for this power method. So, how do we do that? Everything remains same, except that instead of printing the values of y case and c case and x case, we are just returning at the end, we are returning value of x naught and the eigenvalue which is which is computed using Rayleigh quotient. Of course, in this case we saw that this Ck itself will give me eigenvalue. So, therefore, we can simply return eigenvalues as Ck, right. So, this is exactly same, except that I have put this in user defined function, and the name of this is power underscore method. So, input A, the matrix A, x naught is the initial guess vector, and maximum number of iteration is less than 50, tolerance limit is 1 e minus 5, that is 10 to the power minus 5, error, initial error is 1, starting value is 0. Now, this is the maximum number of iterate, and as long as the maximum number of iterate is less than equal to I is less than equal to maximum number of iterate and the error is bigger than equal to the tolerance limit, you compute this, and let me run this, and let us call this function for a matrix A, which is 1 minus 3 1, 3 minus 5 3, 6 minus 6 1, and so on. So, let us run this. So, in this case the eigenvector is this, and the maximum eigenvalue is 3.999. So, this is the what you get, and if you change this, let us say I have this matrix 1 0 1 and 0 1 2 0 0 1. So, this is a triangular upper triangular matrix, and the diagonal entries are 1 1 and 1. So, this means all eigenvalues in this case are 1. So, this does not have dominant eigenvalue. Okay. So, in this case, if you apply this power method, it will still work, but however the convergence will be very slow. So, actually in case of power method, the convergence depends upon the ratio of lambda 2 by lambda 1. So, if lambda 2 by lambda 1, if lambda 2 is small, much smaller than lambda 1, that will go to 0 much faster, right. So, lambda 2 upon lambda 1 to the power k will go to 0 quite quickly in case lambda 2 is smaller, much smaller than lambda 1. So, and in this case, since all our lambda i's are same, the convergence will be very slow. For example, you have to run here 2000 iterates and still it is not very close to 1, right. If I take only 20 iterates, then you have 1.04, which is not very close to 1 numerically, right. So, this is how you compute dominant eigenvalue and corresponding eigenvector using power method. And as I said, this dominant eigenvalue of a matrix has several applications, including Google search, and even the Twitter uses this, and several other algorithm in machine learning like dimensionality reductions, etc. uses this particular notion. Now suppose you wanted to find, let us say, the smallest eigenvalue, and let us assume that the matrix is invertible, therefore the all eigenvalues are non-zero, therefore it will have smallest and largest eigenvalue, of course in mod, and in case we assume that all eigenvalues are real, so therefore and you know that eigenvalue of A inverse is 1 upon eigenvalue of A. If lambda is an eigenvalue of A, then 1 upon lambda is an eigenvalue of A inverse. So if you look at eigenvalues of, if you find dominant eigenvalue of A inverse, that will be nothing but the smallest eigenvalue of A, right. So you can apply power method to A inverse in order to find the smallest eigenvalue of A. However, finding inverse of a matrix, especially for large matrix, is quite expensive task. So in that case, finding inverse and finding the largest eigenvalue numerically will be somewhat quite expensive. So in that case, one can apply what is called inverse power method. And how does it work? So in this case, what we look at is, first we look at some approximation of eigenvalues of an eigenvalue, and then we what we do, suppose sigma is an approximation of eigenvalue lambda 1, which is the largest eigenvalue, and then we assume that this sigma 1 is far away from remaining sigma i's. That is why this modulus of lambda 1 minus sigma is less than equal to sigma lambda I minus sigma in mod for all I between 2 and n, right. So it simply means that sigma 1 is much closer to lambda 1 than any other, right. So this inverse power method is based on this notion. Now if you look at, for example, if if lambda 1 is an eigenvalue of A, then lambda 1 minus sigma will be an eigenvalue of A minus sigma times identity, A minus sigma times identity. So one has to apply this power method to A minus sigma times lambda sigma times identity, the inverse of that actually, right. So what is how this algorithm works? So let me tell you this, the inverse power method algorithm goes as follows. Start with again initial estimate, let us say sigma, it should be sufficiently close to lambda 1, right. Now in principle, how do we select such thing? That one has to do some experiment and then find out this, and one can look at what is the convergence criteria for convergence of these algorithms. Now then you look at, start with x naught, again whose largest entry is 1, a vector x naught with largest entry as 1, set k equal to 0, and then solve A minus sigma times identity yk is equal to xk. So you are solving this particular equation at every stage. Again you can see here, when we want to solve this, solving does not always involve finding inverse, okay. Solving can be done using other algorithms which does not require inverse, right. So instead of finding inverse, we are just trying to solve A minus sigma I, and this you solve for yk, and then define ck to be again the largest component of the absolute value in the vector. In the vector it should be yk, in the vector yk, and then define dk to be sigma plus 1 upon ck, and this ck as k goes to infinity, as k becomes larger and larger, this actually will converge to the largest the eigenvalue, right. And define xk plus 1 as 1 upon ck yk, and then check if the convergence criteria is met. In case that convergence criteria is met, you stop, otherwise increment this iteration by 1, k equal to k plus 1, and go to step number 4, that is again solve A minus sigma times identity yk is equal to xk for yk. Okay. So that is the algorithm, and this algorithm, let us look at how we can implement. So in this case this dk will converge to lambda k, and this xk will converge to the corresponding eigenvector, right. This is since here we are using inverse of this matrix in some sense, that is why it is called inverse iteration with shift method. Shift is the sense here we are using we are shifting lambda by sigma minus sigma, actually lambda minus sigma. So that is why this shift word, right. And if you can notice that the inverse power method is nothing but the power method applied to the matrix A minus sigma I to the power minus 1, that is inverse of this matrix, right. So let us implement this in Sage. So let us take a matrix A which is this 10 minus 8 4 minus 8 13 5 minus 4 4 4, and find out its smallest eigenvalues. In this case we have to say smallest eigenvalue, find out the smallest eigenvalue and the corresponding eigenvector of A, right, using inverse power method, using inverse power method, right. Okay. So again the algorithm will be exactly very similar to what we saw. We import argmin and argmax. This is the matrix. Let us say n is the number of rows in A, and then define the identity matrix. In this case I should say actually n here. This is the initial vector which is 1 1 1, and maximum number of iterate we have taken as 20. If you want you can take, let us say 30, number of digit is 8, tolerance is 10 to the power minus 5, initial error is 1, and sigma value you start with, let us say 1.9, and then I is equal to, start with I equal to 0, and y I is less than equal to n, and error bigger than equal to tolerance limit. You compute y is equal to A minus sigma times identity, the inverse of that into x naught. Now here though I have written the inverse of, find the inverse, but you could apply some other method to solve this. Okay. Since this is not a very big example, this is only 3 by 3 matrix, finding inverse may not be all that difficult, but in principle if you want to implement this for any generic matrix, you should avoid this finding inverse, right. And then again define y mod is the modulus of all the entries of y, I maximum is the argument of the maximum, C1 as y1, that is y0 upon the maximum of the yi, define D1 as sigma plus 1 upon C1 and x1 as y0 upon C0, and then print all these y0, y0, C0 and x1, and then increment I by 1, and then redefine our x1, you store it in x0, and then continue this loop. Okay. So let us run this. When you run this, in this case it requires only 4 iterates, and in this case we have obtained in 4th iterate this is the eigenvector, and this should be eigenvalue. So let us look at what are the eigenvalues of A. The smallest eigenvalue of A is 2, you can see here, and you can also find out what are the eigenvectors of A. So let us find out A dot eigenvectors, right, and so the eigenvalue corresponding to eigenvector corresponding to eigenvalue 2 is 1 minus 2 6, and in this case actually this is, since it is divided by 6, the maximum value you can see here, this is 1, and this will be minus 2 by 6, which is minus 1 by 3, and this is 1 by 6, right. So that is what you have got, right. There are other methods which one can use in order to find eigenvalues, eigenvector. One is Rayleigh quotient iteration algorithm. So it uses Rayleigh quotient, and in this case in fact one can also find other values and eigenvectors, and then the other one is called QR method, which uses QR factorization, and in this case actually you can find all eigenvalues and eigenvectors, corresponding eigenvectors together. Although this method is quite expensive, because at every stage you need to compute QR factorization of a matrix. So that is quite expensive. So but it can in case of a small matrix you can try out. So I expect you all to go through this method, look at help on these methods and try to implement it in Sage, right. Let me leave you with 2-3 simple exercises. Find the largest eigenvalue and corresponding eigenvector of this matrix using power method, and this is the second problem. Next one is find the smallest eigenvalue of A and the corresponding eigenvector using inverse power method. So these are the 3 simple exercises. We have already written user defined function for each of this, though we have not written user defined function for inverse power method, but I am sure you can just make small change in this syntax and convert into user defined function. Okay, so let me stop here. This is how we find numerically eigenvalues and eigenvector, which are dominant eigenvalues and eigenvectors, and it has several applications in science and engineering. Thank you very much.